right, in section 1, we are going to talk about chemical reactions. We start with definitions. The first of which is, what is a chemical reaction? When I write reaction moving forward, I will write RxN. So this is going to be a process. Where one substance or more become a different substance. When we write chemical reactions, we write them so that the reactants are on the right, on the left, and the products are on the right. Some rules for chemical reactions, really the big rule. According to the law of conservation of mass, what is present at the beginning must be present at the end. In other words, if I start with compounds containing carbon, hydrogen, oxygen on the left side of the equation, I must then end with compounds containing carbon, hydrogen, and oxygen on the right side. Can't just create something from nothing. So no sodium just kind of popping up or anything like that. Okay. A chemical reaction will contain the formulas for substances. On both sides. So there's a chemical reaction written with reactants, products. Some other things that we're going to see in chemical reactions are symbols, which you did talk about yesterday. And we'll talk about here in a little bit. But for now, understand this is what we're going to be studying in this particular section. We're going to study the anatomy of a chemical reaction. Okay? This arrow has a literal definition of the term yields. So when we talk about chemical reactions, we say the combustion of something yields something new. We don't really use creates. Sometimes we can use like reacts with to form. But for the most part, that arrow is meant to say the term yields when you're reading about chemical reactions. From there, we can talk about the indications of a chemical reaction. And you've seen these before. So we're looking for chemical changes, essentially. The first is light. being produced. Along the same lines as heat. Those are the same idea. Where there's light, there's heat. Where there's heat, there's light usually. They're kind of interchangeable. The next one is going to be gas production. So if something bubbles, it means gas was produced. The next is going to be what we call formation of a precipitate. The term precipitate means solid. When a reaction happens, if a solid is formed, it is called a precipitate. The last is going to be probably the most obvious, which is color change. Put two white powders together and get a green one, something happened. Likely a chemical reaction. What's next? Okay. I'm going to erase these so that I can write about them up here. Okay. The anatomy of a reaction. One of the requirements for us to label it a chemical reaction is that it must represent known facts. Don't just make stuff up off the top of your head. When we write chemical reactions, they represent actual reactions that can occur. That is rule number 1. Rule number 2. The equation, so this is called an equation, chemical equation, right? Must contain the correct formulas. For both reactants and products. Real quick, this is why yesterday, when you were writing your formulas for what you were working on, you were not just supposed to write this. Okay? Because that's not how those things would really combine. The real formula for aluminum combined with nitrogen would have been based on its charge. So when those two things come together, when an aluminum atom comes together with a nitrogen atom, we learned in chapter 7, it's based on the charge. Okay? So what's the common charge of an aluminum atom? What's the common charge of a nitrogen atom based on its location? -3. When we're trying to predict what the product of a reaction is, we have to use those things we know to predict that. This would get us this. That's not immediately obvious when you were given these two things, right? You had to actually do some of that back work that we talked about in chapter 7 to figure out what the appropriate formula for that particular product would be. Yes?
So does the 2 not matter?
The 2 doesn't matter yet. We're learning what the 2 does today. Okay? Okay, so that's what we mean when we say the equation must contain the correct formulas for both reactants and products. For the most part, in this chapter, we will be dealing with equations that are given. You would be given the equation, overall, reactants to products, okay? The predicting of things comes later. The next one. The law of conservation of mass must be obeyed. This is why we balance. So that's where we're going to go next. When we balance chemical equations, we're going to use coefficients. So that was your question today, right? What is a coefficient? What is a coefficient? Yes?
It multiplies it goes before the element and it multiplies by whatever number it is.
In the equations that we're going to look at, coefficients are the numbers that come before the compounds. So there's only one visible in this reaction, right? That 4 is my one coefficient. Are there coefficients in front of each of these? Yes, there are. What are they? 1. Remember that in chemistry, just because the number's not there doesn't mean it doesn't exist. It just means it's probably a 1 or a 0. In this case, it's a 1. Okay, let's look at some other pieces of information we have to remind ourselves about. The first of which is the diatomic elements. What are the diatomic elements? Starts with hydrogen. These are, but first before we name what they are, what does that mean? Diatomic means they're found as twins. Let's call them twins. Meaning they're never by themselves in a reaction. Oops. So H2, O2, N2, F2, Cl2, bromine, and iodine. Someone mentioned that it makes a little 7. It's kind of cool. I've never seen that before, and I've been looking at periodic tables my whole life. So you start at the 15, and you go over, and then down through 17. You see a little 7. It's kind of cool. Plus H. Just don't forget to add H to that group. What that means is these will never be, right? So you should never see this. This is not a thing. You never see them by themselves in a chemical equation. They're always with a part.
Oh, what happens to the element's charge?
That's a good question. These are what we call elemental. Charge is 0. So when we saw in our equations the other day, metals can be alone. They're usually like this, okay? We say they're in their elemental form because they're found the way they're seen on the periodic table. So they're neutral, so their charge is 0. We also learned that some reactions have the charges change from one side to the other. Don't worry too much about it yet, but those are single displacement reactions. Nothing else really does that. Yes? Well, go ahead.
Is there going to be like the elemental forms in the products of a reaction?
They can be on either side. Elemental forms can be on either side of a reaction. There's no rule about that. Go ahead.
So with the 2,
Yeah.
is that charge going to be 2?
No, there's no charge. These are going to be 0 charge. They're neutral. It's like saying, so if I write Fe on the board, right? Like, let's do this. If I write this, that has a 0 charge, right? Okay. If I write this, that also has a 0 charge. When it's in that form only. Now, when oxygen is combined with something else, its charge is typically what? -2, right? So it only applies when they're by themselves. Okay. Do. Ready to balance something? Can I erase this? Okay. Okay, so let's look at a chemical reaction. Okay. One of the things I want to point out are symbols in chemical equations before I get too far and what they mean. And you kind of did this in your activity yesterday or the other 2 days. Where if you see these kinds of things, they indicate the state of matter that chemical compound is in. So aqueous means dissolved in water. S means solid. L means liquid. Mine look kind of weird, but they're supposed to be like cursive L's, so that's why I write them that way. And then G means gas. All right. So these are like the really basic symbols you'll see after the different chemical compounds in an equation. What are some other symbols you might see? So we already said the arrow, right? What does the arrow mean? Yields. What does that one mean? Starts with an R. Reversible. Okay, so let's do some more challenging ones. Ooh. I'm just gonna keep going over here. Okay. What does that mean? Heat. It means heat applied. So if I put a delta up here, it means I took these two things, added them together, and I applied heat to this particular equation to make it happen. Okay? That's not what we're doing. Okay? You got pressure, which means what? Typically, when we write this, we would give a value. So it means do the reaction at a pressure of 2 atmospheres. Okay? Whatever pressure is given. Similar thing can happen with temperature. Do at the temperature it's given. We've got, this is more common in organic chemistry, but this, any kind of like a compound listed above an arrow is a catalyst present. And that thing at the top tells you what the catalyst is. In OChem, it's commonly just platinum. Okay, what do catalysts do? Anybody remember? Speeds up the reaction. I like it. Okay. All right, so let's talk about balancing. Who remembers? Kind of, sort of. Have a vague idea. What's the goal of balancing an equation? Go ahead, Anna.
Get like the same amount of each atom on each side.
Right, so if I have one carbon here, I want one carbon here, okay? So for balancing equations, what we're gonna do, and it's the method that I teach to anybody who's never done it before, I'm gonna draw a line underneath the equation that separates the two sides of the reaction. Okay, think of this like a scale. I've got to get this side to balance this side. Is that the Libra symbol? You're welcome. 'Cause I'm a Libra. All right, so this side and this side have to equal each other. That means the number of atoms on this side has to equal the number of atoms on this side, the total number of atoms, and the type of atoms. This type of an equation is a combustion. Did you spot that? Combustion equations are some of the more challenging ones we will balance. This is not a challenging one that we will balance, but they do get more challenging. We'll talk about the special way to treat them here in a little bit. Okay, so what I'm going to do is anytime I balance an equation, the first thing I always want to balance is going to be a carbon if it's present. What I'm going to do is I'm going to draw a list on either side of the different atoms that are already present. So I've got carbon, hydrogen, and oxygen on both sides, right? Do I have any others? Nope. Okay. So on the left side, the first thing we do is a count. So we're going to do some counting. How many carbons do I have total? One. How many hydrogens? How many oxygens? All right, now we move over here. How many carbons? One. How many oxygens? How many hydrogens? Okay, so that's a problem. Our goal is to get them to balance, right? The carbons are already balanced, so I don't need to do anything for that. Sorry, usually I draw my little things in front. Those are for my numbers, okay? All right, well, let's try to balance the hydrogens. How could I do that? By just manipulating numbers in front. Anything I put in front multiplies the stuff inside. So I can put a 2 here, right? If I do that, anytime I change a number up here, you better be changing numbers down here. And that includes double checking every single atom. Did my carbons change? No. Did my hydrogens change? Yes. On this side, I'm at 2 times 2 is 4. Did my oxygen change? Yes, it did. It went from 3 to 2 plus 2 is 4. We're getting closer. Do these numbers match? Do these numbers match? Does this number match? No. How do we get more oxygens? I wanted it to be 4, right? So I'm going to put a 2 in front. 2 times 2 becomes 4. Now are we balanced? You don't have to double check if you use this method. As long as you are balancing equations, use something erasable. Pen or pencil, I don't care. And as long as you are counting after every time you put a coefficient together. Make sense? Okay. Let's do another one. One of the things I do want to point out here is I don't put numbers in front, but what number does go here? A 1. A 1. One of the most common ways that I can ask questions with balanced equation is, what is the sum of the coefficients of a balanced equation? Okay? For this particular exercise, what would the sum of all of the coefficients be? If you don't put the 1s and you write a 4, that's wrong. Do you see? Okay. So just because you don't see the 1s, just remember they're always there. And at the end of balancing, go back and fill them in if that's going to help you. All right. Da-da-da-da. This is somewhere in your notes, I would like you to write this. Please. Somewhere in your notes, I'd like you to write that. It's the same exact thing. It's just a different way of writing the formula for water. The way that I've written it on the right, though, shows you that OH is a polyatomic ion, right? The way I've written it on the right, it's easier to break apart and see when it breaks apart when we use equations sometimes. In this particular case, let's start. We're going to start with the non-oxygen hydrogen thing. We're going to list them both on both sides. All right, let's start. First things first. How many sodiums on the left? 2. How many oxygens? 2. How many hydrogens? Oh, that was easy. All right, what about on the right?
1.
Okay. Well, what should we do?
Maybe put it two.
Oh, just put it 2. All right, what happens? Are they going to be that easy most of the time? Probably. Seriously, a lot of times they're very easy like this. It's like, oh, I just need a 2 here, or I need a 3 there. It's not always going to be super intense. Okay, let's do. I'm just looking at the options. I have options. I don't know. Okay. That one's too easy. How's that one? Ooh. Ooh. All right, okay, so we're going to take a break from balancing and talk about some things too. We've got to talk about a couple of things. But first, what kind of information can we get from chemical equations that is quantitative in nature? Coefficients are very useful. They give relative, not absolute, info about amounts of reactions. Relative amounts of reactants and products. In other words, we're going to reference this one. In other words, what it tells us is that you need a 2-to-1 ratio of amounts of H2 to O2. 2 being the number in front of the H2, 1 being the number in front of the O2. You see that? So when I'm trying to do this reaction, coefficients will tell me approximately in relation to each other how much do I need. I need double the molar amount of H2 versus O2. And this is molar amount. In other words, I need 2 moles of H2 for every 1 mole of O2 to produce 2 moles of H2O. Okay? I'm going to rewrite that for you. 2 moles of H2 for every 1 mole of O2. kind of reaction is that? Thank you. Woo. Trucking right along through section 2. I heard section 3 is really short. It's like 2 or 3 pages. Yeah. Okay, so that's the first thing we can get. The second thing is that we can get the relative masses of the reactants and products of a reaction can be determined from the coefficients. That's common for you in chapter 9. In other words, what we're saying is we can use the coefficients of a chemical equation to determine mass information. So if I, for instance, am given a mass of hydrogen gas that I started this reaction with, I can use those molar amounts and molar masses from the periodic table to determine what mass of water should be produced from that mass of hydrogen I started with. The big word for that is stoichiometry. The process for that is called stoichiometry. We're going there. We're not there yet. But understand that this is the second and probably arguably, in my opinion, the most important piece of information we get from chemical equations. This takes a chemical equation from just being written on a piece of paper to being done on a bench. Okay? And that gives us a predictive method for how we can determine how much we should have produced if we put the amounts we put together. All right, last but certainly not least, the reverse reaction. For a chemical equation has the same relative amounts of substances as the forward reaction. In other words, if I flipped that reaction around and made it a decomposition reaction, the molar numbers stay the same, and we can get the similar information. We're just doing the opposite process. Reversing the reaction does not change the outcome. Okay. Stuff we don't get from chemical reactions. 1. Whether or not it will occur. There is no indication in this chemical reaction of whether or not this will actually happen. We just wrote that on the board, right? I could be making that up off the top of my head. Not supposed to do that, but there is no indication that this would even happen if I tried it. I do not get that piece of information from the chemical reaction itself. I get that from experimentation. All right, next. We will not know how quickly it will occur. We get no information about bonding. Yes.
Are chemical equations and chemical reactions the same?
Yes. Sorry, I use them interchangeably on purpose. They're the same. Chemical reaction just implies it actually happens. Chemical equation is the proposed version of a reaction. We use the same. What other questions do we have? Doing okay so far? We will practice balancing chemical equations until you're dreaming about them, don't worry. Let's find a hard one. Want to do a hard one? Yeah. You ready for challenge mode? You got this. I believe in you. Sorry, I didn't ask. Does anybody need something to... Too late. If you missed something, let me know. I'll send you my notes. Okay, sound effects. Here we go. And this is a solid. Start by cutting them in half. In this particular case, I am going to write this. I think it will help, not hurt. Because when it comes to balancing polyatomic ions, I want to keep them together if they're present on both sides. We're going to call this the hints section, guys. All right? Hints, tips, tricks, all that kind of cool stuff when it comes to balancing equations. Here's your first one. Well, second one, because the first one was the H2O equals HOH. Okay? The second one is if a polyatomic ion is present on both sides, balance it as if it's by itself. Balance as is. Okay? So in other words, what that means is, I'm going to write out my values. I'm going to leave it like that when I try to balance it. The only reason this works is because I realized that OH is here and OH is here. If that were not the case, I couldn't use this particular trick, okay? But it will save you a headache if you can recognize the polyatomic ion is present on both sides as it's supposed to be. You can balance it as if it's on both sides like it's a polyatomic ion. All right, we'll start with aluminum. How many here? Carbon. Hydrogen. One. OH. There's one. Okay, let's do the right side. How many carbons? One. Hydrogens? 4. Aluminums? 1. And OHs? 3. Oh boy. All right, so again, whenever you list them, I listed them left to right, didn't I? As I went down. I would just start at the top and work my way down. I, as a person, try to leave hydrogens and oxygens for the end on purpose. And there's a rhyme and a reason to that, especially when we get to combustion reactions. For any reaction that isn't a combustion reaction, you can balance them in any order. I'm going to do it this way. Could you do it your way? 100%. Just want to make sure you understand. There's no reason to start with aluminum. I'm just going to start there because I put it at the top. All right, so I have aluminums 4 here and 1 over here. That's a problem for me. So what am I going to do? I'm going to put a 4 here. Then I'm going to do my accounting. I now have 4 aluminums on the right side like I was going for. But what other number should have changed? My OHs. How many of those do I have? 12. Wow, that's a lot. Okay, I've got 3 carbons on the left. How many should I have on the right? 3. How do I get a 3? We put a 3. What does that do to my hydrogens? I'm not trying to go fast. If I'm going too fast for some of you, you can always tell me. Okay? All right. My first 2 numbers are balanced. It's the last ones that look like they got to get balanced. Hey, look at that. They're together. What do I do? Am I balanced? Okay. Remember, always add the 1. Questions? Issues? Nope. Okay, well, that's all I have for you today. We'll talk about more tomorrow. Look at that, you made it through.